sensor data. This research was done under the guidance of Dr. Raghuvanshi sir. Let me introduce to the problem. Internet of Things networks consist of huge number of sensor devices to sense and report various sensor readings of the corresponding environment where they have been deployed. The volume and velocity of the data generated by these sensors are huge over a period of time. Due to the deployed environment or cause of the abnormal events in the observing environments, the reported data consists of noise or outliers. Outliers or noise can be said as anomaly. An anomaly is a deviation or exception from the normal value. An anomaly is an occurrence that occurs infrequently or does not fit the model and thus appears suspicious in the collected data. The objective of our research was as sensor data generated by various wireless sensors which has multiple distinct features. Sensor networks have recently become a popular topic of research study, particularly from the standpoint of data processing. Sensor network data anomalies could indicate that one or more sensors are malfunctioning or that they are detecting events that are of interest to analysts. As a result, sensor network anomaly detection can detect sensor failure, infiltration, or even both. Sensors that capture binary, discrete, continuous, and other types of data can all be found in a single sensor network. The data is also dispersed, necessitating the use of the distributed data mining approach to examine it. To this end, this paper proposed to study three deep learning models, which are autoencoders, long short-term memory autoencoders, and long short-term memory recurrent neural networks for detecting anomalies in time series IoT sensor data. Let me present you some related work. One of the authors presented use of the deep autoencoders for outlier detection. Authors proposed active autoencoders to break through the bottleneck problem of the conventional autoencoders. AAE approves autoencoder performance by combining inference-based active learning with a novel way to change simple sample weights using the expansion shrinkage operator. Another author proposed study with two-phase deep learning model for short-term wind direction forecasting. Authors proposed a two-phase short test wind prediction model using DL methods. In this, authors performed hybrid data processing by improving echo state network for prediction modeling. The flower pollination algorithm is improved to optimize the echo state network's parameter. Another author presented that to detect anomalies in network traffic data, autoencoders and they use autoencoders and OCSVM, which is a hybrid model. In this work, authors proposed model replicates the input data to output data, which possess low reconstruction error and is unable to replicate the data which are given high error rates and hence can be written under the column of anomalies. Now the deep learning methods which we use for our research paper. First was autoencoders. An autoencoder is a type of artificial neural network used to learn efficient codings of unlabeled data. The encoding is validated and refined by attempting to regenerate the input from the encoding. The autoencoder learns a representation, which is the encoding, for a set of data, typically for dimensionality reduction, by training the network to ignore insignificant data, which can be called as noise or an anomaly. Variants exist, aiming to force the learned representation to assume useful properties. Some of the examples are regularized autoencoders, which are effective in learning representation for subsequent classification tasks, and variational autoencoders with application as generative models. Autoencoders are applied to many problems, including facial recognition, feature detection, anomaly detection, and acquiring the meaning of words. Autoencoders are also generative models which can randomly generate new data that is similar to the input data. The second model is LSTM autoencoders. An LSTM autoencoder is an implementation of an autoencoder for sequence data using an encoder-decoder LSTM architecture. For a given dataset of sequences, an encoder-decoder LSTM is configured to read the input sequence, encode it, decoded, and then recreated. The performance of the model is evaluated based on model's ability to recreate the input sequence. Once the model achieves a desired level of performance, recreating the sequence, the decoder part model may be removed, leaving just the encoder model. This model can be used to encode input sequence to a fixed length vector. The resulting vectors can be then used in a variety of applications. Next model which we used is the long short-term memory. Long short-term memory, also known as LSTM, is an artificial neural network used in the fields of artificial intelligence and deep learning. Unlike standard feed-forward neural networks, LSTM has feedback connections, such as recurrent neural networks can process not only single data points, but also entire sequence of data. The name of LSTM refers to the analogy that a standard RNN has both long-term memory and short-term memory. The connection weights and biases in the network change once per episode of training, analogous to how physiological changes in synaptic strength store long-term memories. The activation patterns in the network change once per time step, analogous to how the moment-to-moment change in electric firing patterns in the brain store short-term memories. The LSTM architecture aims to provide a short-term memory for RNN that can last thousands of time steps, thus long short-term memory. Now the simulation setup for our research. Intel Berkeley Research Laboratory sensor dataset is considered to evaluate the deep learning models presented in the previous section. IBRL dataset is a well-known benchmark dataset that is widely considered for experimentation by researchers. This dataset is the collection of sensor readings of 54 wireless sensor nodes placed in different locations of IBRL. This experiment was conducted at IBRL from 28 February 2004 to 3 April 2004. Readings such as temperature, humidity, light, and voltage of each sensor node were collected for every 31 seconds for the whole duration of the experiment. Out of these 54 nodes, node 5 and 15 have not recorded any reading during the experiment time. Hence, we have not considered the node 5 and 15 for the present work. The IBRL dataset consists of features such as temperature, humidity, light, and voltage. We have considered temperature readings for conducting evaluations. The considered dataset is added with a few more features such as hours, day of the week, weekday, and daylight, along with the existing features, daytime and temperature. With this, clear information of variation of temperature readings were fed to the deep learning models LSTM RNN due to its advantage of handling multivariate data. On the other hand, autoencoders and LSTM autoencoders are inputted with the scale temperature values. Since the data type of the added new feature and the existing features are different, we have performed normalization of the data with the min-max scaler to work with autoencoders and simple scalar operation to work with LSTM autoencoder and LSTM RNN. Training and testing sets were created using the normalized data, and the training data is sent to the deep learning models. Now let us discuss the results of our experiments. Firstly, we'll discuss the results of autoencoders. It was observed that around 114 data items are identified as anomalies, while there exist only 100 actual outliers. It is observed that the average training time of the autoencoders is observed as 268.8 seconds. It is also observed that the training time increased with respect to the increase in the denseness of the layers in the autoencoder. Now the results of the LSTM autoencoder model. It is observed that around 110 data items are identified as anomalies, while there exists only 100 actual outliers. It was also observed that the average training time of the LSTM autoencoders was 186.8 seconds. Now the results of the long short-term memory LSTM RNN. It is observed that around 102 data items are identified as anomalies, while there exists only 100 actual outliers. It was also observed that the average training time of the LSTM RNN was 3,397.7 seconds. To conclude the results, the accuracy of the LSTM RNN model was the highest, which is 99.72. But on the other hand, the training time for the LSTM RNN was also the highest. Autoencoders accuracy measure was 87.8%, and the training time of 263.8 seconds. With the least training time was the LSTM autoencoders, which is 86.8 seconds, which showed the accuracy percentage of 90.9. The conclusion and future work related to our project. We proposed a study on the functioning of three deep learning models, namely autoencoder, LSTM autoencoder, and LSTM RNN for detecting anomalies in the Internet of Things time series sensor data. The study was concluded using the benchmark IBRL sensor dataset. It is observed that in the deep learning models, the conventional autoencoders are exhibiting faster compilation and training. On the other hand, by using LSTM autoencoder, it is found that compilation of the model and training is as faster as autoencoders, with the difference of increase in prediction accuracy. LSTM autoencoders are working good as compared to conventional autoencoders. The third model, LSTM RNN, outperforms other two models in predicting the data values. In spite of this advantage, it is observed that LSTM RNN is taking long time to train as compared to the other two models. With these observations, as future work, we attempt to investigate other deep learning models with huge and multivariate datasets. Thank you.
Thank you, Ujjwal. Any questions, please? Any questions? Okay, Ujjwal, I have one question. In time series analysis, it is important that the data is stationary as well as it has no autocorrelation. So, was your data stationary? And if not, how you have dealt with it?
Ma'am, the data was not stationary. As I mentioned in the presentation, the data was collected every 31 seconds in the while performing the experiment. So, in order to deal with this continuous data, we first performed the using LSTM RNN model, and there we inputted the sample data as for some duration, like not for the whole period of time. For some duration, we inputted the data and checked the results for that sample of time.
Was there any specific algorithm used to make the data stationary or something like that, or you have just done what you have just explained?
We have done with what just I have explained now.
It is normally expensive to train the models in time series. So how many features in one go you have taken for the training purpose?
We have taken only the temperature data to conduct our experiment.
Okay. Thank you.
Thank you.
So